Okay, I think this is recording now. So my name's Simon Josie. I'm based at the National Oceanography Centre in the UK, and I've been asked to invited to talk on air-sea fluxes in models. So I've actually modified that slightly. I'll be talking about air-sea flux moorings and how I've used them and how people more generally are using them to evaluate models and models reanalyses and the joint insights that we can get from these resources. So first of all, I'll talk about how the ocean sites observations have enhanced my research, and then ask about the societal benefits of the observations, and then deal with where the gaps are and what those gaps are and where we want to be in 2030. So my research tools are observations, I should say to start with, cutting edge observations from the moorings and atmospheric model reanalyses, and I try to combine those wherever I can. And unfortunately the slide isn't working, but it is now. Okay, this is the very first time I should say that I'm trying to record a talk, so any glitches, please bear with me. So first of all, some research highlights, some highlights of my research looking at the Irmingham Sea. And this is, I've used moorings over the last 25 years, many locations globally. And this recent research has been carried out in the Irmingham Sea at one of the ocean sites using Ocean Observatory's initiative mooring. And I should make the point straight away that I've had nothing to do with the deployment or the development of these moorings. I'm just a lucky guy who gets to use the data. And I want to give full credit to Bob Weller and his team at Woods Hole and other institutes around the world, the people who put all these moorings out and put a great amount of time into doing that. Anyway, let's come back to this this story and say, why are we interested in this region? Well, we're interested because mid to high latitude processes of air-sea interaction are very important for driving ocean variability, and this variability can feed back on the atmosphere and it can modify the weather of surrounding regions. Now, air-sea flux observations at these latitudes are extremely challenging. It's typically bad weather. It's a long way from normal trade routes. So we don't have ships of opportunity going there and very few observations of meteorological conditions. So until this Ocean Observatory's initiative mooring was deployed, we really didn't know much about what was going on here. There have been some earlier shorter term studies, order months in length, and there have been plenty of model studies which indicated that the Irmingham Sea was a region where intense atmospheric jets could affect the heat loss, but we didn't have any multi-winter observations of heat loss. And that's what we've gained from this mooring. And we've been able to carry out an analysis which has provided the first multi-winter characterization of the air-sea flux variability in this region. And it's revealed very strong variability. And by a joint analysis of the mooring data with models, with model reanalyses, we can see that that's related to the formation of these very strong tip jets, which don't occur every winter, but when they do, they drive very strong heat loss. And we've also looked at what determines the frequency of the tip jets and found a new large-scale relationship, again using model fields, model reanalysis fields. And in this particular example, hopefully you can see my cursor there, there's a mode of variability called the East Atlantic pattern, which generates an atmospheric circulation anomaly that acts in the sense to suppress the tip jets and suppress the dense water formation, and so potentially important for the ocean circulation. That work's all written up in GRL last year. And just to forward the slide, there we go. So now let's move to the other end of the global ocean down south. I've worked looking at moorings in the Southern Ocean, two moorings in particular, one the Southern Ocean Flux Station south of Tasmania, put out by Eric Schultz, maintained by him for a long time now, and another one more recently. So that was deployed 2012, this one in 2015, the Ocean Observatory's initiative mooring, which sadly is no longer there as it's been withdrawn. Now that's a problem for us. Both of those moorings provide observations in, again, an extremely data sparse region. Unfortunately, I've gone back a slide now. Let's go forward 2 slides. There we are. So these provide us with information which we simply didn't have before. And with that information, we're able to get new insights into processes linking the heat loss to mode water formation, for example, This OOI site, which you're seeing here, is in a mode water formation region. It's also in a very data sparse region, very few dots nearby from ship observations. Time series at the bottom showed they were typically in the months, this is the years 2015-16, within 500 kilometers of the site. There were only a few observations, 2 or 3 per month from ships. Suddenly we leapt to 120 6-hour observations per month, which in turn were based on 1 minute values. So just an incredible richness of data. And that was analyzed in a paper led by a student, Sarah Ogle at Scripps. And encourage you to read that one for more detail. I won't go into the details of this figure, but I think it's one of the figures from the paper, and it shows the daily mean air sea heat flux actually measured by the mooring, and that's it converted into monthly means. And we could see, for example, that there were, in some winters we had very strong heat loss, in other winters we had weak heat loss, and looked at the impacts on mode water formation. We've also done something where we've combined the data from 2 moorings. So rather than look at the moorings in isolation, in a recent analysis led by Veronica Tamsit, we look at joint heat loss at the Southern Ocean Flux Station site and the Ocean Observatories Initiative site. And interestingly, we found 2 main regimes for mode water formation. So we can either have, as shown in the top panel, strong heat loss at both sites, the blue colors here. That's when we have a joint wind directions from the southwest, bringing cold, dry air over the sites. And so now we have, under this regime, coordinated mode water formation at the 2 sites. And then we have another regime where we just have strong heat loss at the SOS site, and that's because we have a pressure pattern which enables cold, dry air to move up from the south and then to recirculate, still cold and dry when it comes onto the mooring from the west and northwest. But the corresponding direction at the OOI site is associated with warm, moist air. So here we have the mode water formation at the 2 sites uncoordinated. Okay, so these are examples of my research, and in the last few minutes I want to talk about the benefits and a bit about the gaps in the left at present. And looking at the North Atlantic first, I've told you a little bit about this. One of the big things is to identify processes that are potentially missing in the current generation of climate models, the one we use for our climate projection, currently CMIP6. And the example I give there is this relationship between the tip jets, which are local scale, likely very poorly represented in these coarse resolution models, and relationships between those and the larger scale atmospheric modes, which are better represented. So we can identify this relationship using the observations, but we can, and then we can test whether it's there in the coupled models, and if they're representing it poorly, we can make advice for subsequent generations of models. And ultimately, all of this feeds into a better representation in climate models of dense water formation, its impact on the overturning circulation of the Atlantic, and hence more accurate projections of climate change into the future. Likewise, in the Southern Ocean, we have a better understanding of controls on mode water formation. That mode water takes up heat and takes up carbon. And again, this is another key element of the climate prediction problem. More generally, I think in Lee-San Yu's talk, you're going to hear more about anchoring of flux fields using moorings. This is a key thing. So essentially evaluating flux field accuracy and then potentially using the accurate mooring observations to improve the accuracy of flux fields. This is incredibly important, both for getting new insights into the underlying air-sea interaction processes, but also because fields based on the atmospheric model output are used for forcing ocean models. So that eventually enables a more accurate model simulation of key processes, for example, the re-emergent temperature signals, which may have an impact subsequently on climate. So final slide, this is now looking at gaps and where we should be in 2030, and I think we'll elaborate on this in the discussion. So I've taken a figure from the Ocean Obs 19 meeting SE Fluxes chapter that Megan led, and she put a lot of work into this. It's a very interesting chapter, and I urge you to read that. And one of the things it does is it identifies high priority sites which are currently without flux reference stations. So I've modified, sorry about that, let's go back a slide. I've modified the figure slightly. So what we're seeing here on the original figure, the black squares, which are currently occupied sites, although I should say some of them are no longer occupied, the OOI site in the Southern Ocean being one which has been vacant now for nearly a year. But also on here, I've added some green crosses, and those green crosses indicate the sites which we proposed as being high priority in that chapter. There's a list of them there. I won't go through the details. You can look at it in more detail afterwards, but it outlines the key processes at each site which we want to get a handle on, the reasons why we've chosen those sites. Okay, and I'll close just by saying a bit about something else as well. So long-term goals to fill these sites, but short-term goals, we need to worry about how we use that mooring data, and there's an issue we need to address, which I call here the spatial scale mismatch problem. So what we have here is we're using point measurements from moorings to evaluate reanalyses, which can have a grid scale of 25, well, that's very high resolution reanalysis, to 250 kilometers, say. So how do we know whether the mooring data is representative of what the reanalysis thinks is happening at that much larger scale? Are there useful approaches? I've seen recent papers using transfer functions in another application. Can we use such approaches to apply this to this scale mismatch problem? And that's something for discussion, I think. Okay, so I'll end there. Hopefully this is recorded, and because it's my second attempt, and hopefully you'll be able to enjoy it online if I can stop the recording. So just ignore this part until I stop it, which I'm now about to do. And I've